So in this presentation, you will learn something about cut resistance of climbing ropes, how dangerous rope cuts really is, how different companies are trying to develop methods to measure cut resistance, and that rope cutting is not as simple as it may seem, but there might be multiple braking mechanisms involved at once. So let's start with one video. If you have seen it. Yep. So this is quite uniquely filmed video of a rope cut accident from 2017. I can say luckily the climber survived, broke his wrist and ankle. But unfortunately, those accidents don't always end with a happy end. So the rope cut is a problem. The question is now, how often does it happen? This is statistics that colleagues from Edelrit, German sports company, compiled. And for example, in the last 10 years, around 5 accidents per year are reported. I emphasize the word reported because even I have friends whose rope was at least partially cut, and because of that they were in danger. And we have to see this also in the context of the fact that rope manufacturers never really focused on cut resistance. So maybe by improving cut resistance a little bit, we can just save lives. Fortunately, in last years, companies like already mentioned Edelrit from Germany or Mammut from Switzerland or International Climbing and Mountaineering Association developed and are proposing methods how to measure cut resistance. So I will show you them in next slides. This is the method from Edelrit. The rope is in a tension with a force equal of around 100 kilograms, and in the middle is a sharp steel disc which rotates and cuts the rope through. The second method is the method from Mammut. The rope, I hope it's visible, rope is here in the middle from top down. It's in a tension with a force equal of 1000 kilos, so 10 times more. And it's cut with a pendulum swing where the sharp steel blade is attached on the pendulum. And the last, third method is the method from International Climbing and Mountaineering Association, so-called sharp edge drop test. Actually, on the video, there is a standard drop test. This sharp edge drop test looks the same. Only this ring here, which simulates the carbine, is replaced with a steel sharp edge. Otherwise, it looks the same, and the rope breaks during the fall. So you may have noticed that all those methods are quite different. 2 methods are static, 1 method is dynamic. The forces in the rope varies greatly, and all those parameters have a big influence on which braking mechanisms are actually involved during cutting. And that was my research question. Which braking mechanisms on the fiber, on microfiber level are involved in those tests, and how it compares to real climbing situations? That's why we decided to do a simulation of climbing accidents, which look like this. That's me. Don't look at those ropes. Those ropes here are just to prevent the falling concrete block hitting the ground. The rope tested is this thing on here. And there is a real granite edge stone with a sharp edge.
1, 2, 3.
Okay, that's it. So we have those 4 methods: the cutting disc method from Edelrit, pendulum method from Mammut, the sharp edge drop test from the International Climbing and Mountaineering Association, and the simulation of a rope cut accident. And what I did that in order to investigate those braking mechanisms, I broke the ropes and I was looking at those broken fibers under the microscope. This is how it looked like. I found 4 distinct braking mechanisms, which I will explain you briefly now. The first one is, I call it a clean cut. Here's the detail. I would explain this mechanism as when you are cutting mozzarella with a knife. We have something sharp, we have a pressure, we have a sliding movement, and the object just cuts the through. That's why the fibers are so nicely cut without any deformation. The second one is, I call it blunt cut. You can imagine this one as you would cut the mozzarella not with a knife, but with a saw. So on a macro level, it looks the same. That you have some object, you have a pressure, you might have a sliding movement. But as you can imagine, on the micro level, because of the structure of a saw, you have different mechanisms. That's why the fibers are kind of squeezed and they are not really cut, they are kind of teared. The third mechanism is very different because it does not involve any sharp edge. It's called high-speed tensile brake, which forms such as mushrooms. This occurs when the fiber is stretched really, really fast. It heats up because of this stretching, and then when it breaks, it's in kind of quasi-molten state, and it snaps back and forms this mushroom. Yeah, so no sharp edge involved, only high-speed tension. And the fourth one is a little bit mystery for me now. It's still under investigation, but I found often those molten fibers fused together. I assume that the process might be similar as the second one, as blunt cut, but maybe the speed of the cutting is faster, which produces more heat due to friction. But there might be other processes involved, like, for example, the fibers might be in quasi-molten state because of the fast stretching, and then when something cuts through, it can theoretically make the same appearance. But in general, we have those 4 braking mechanisms here, and I assigned those icons to each of them, and I will use those icons in the next slides in evaluation of the methods I used. The first, I would divide the rope into 2 pieces. It's a sheet and core, and for those who are not familiar with the rope construction, the core is the inner part of the rope, and the sheet is this surrounding outer part of the rope. So I was looking separately on many regions, but for this presentation, I summarize it into the core and sheet. So after the NLE test, I found those clean and blunt cuts in the sheets, and the same in the core. After the test from Mammoth, in a sheet I found only high-speed tensile brakes, and the same in a core. So we can already see that those methods are quite different. This sharp edge drop test in a sheet, I found high-speed tensile brakes, and in a core, actually multiple braking mechanisms at once, dominated by high-speed tensile brakes. Okay, those were the 3 laboratory methods, and now the simulation of climbing accident. In the sheet, I found those blunt cuts followed by molten fibers, and that's a braking pattern which didn't appear in any of those tests. And in the core, I found like a similar multiple braking mechanisms as in a sharp edge drop test. So what is the conclusion? The conclusion is that it matters how you cut rope and how you test it, because different braking mechanisms are involved. And if you will try, for example, or if you will try to improve cut resistance of ropes by introducing new materials, for example, one method may show you improvement in the cut resistance, and another method may show even decrease in cut resistance. And that's why we need to carefully develop new methods, how to measure it. And then when we will have these methods, we can make the ropes safer and we can save lives. That's all from my side.
Oh, they are raising hands. Let's take them. Yeah.
So, yeah. Are we seeing very different rope perform very differently in all the tests? Like we took a rope from Beal, one from Mammoth, one from Sterling, for example, and ran all 4 tests on them. Are they all performing very differently in those scenarios?
Very similar. Actually, I was in cooperation with Mammoth, and we tested actually 6 ropes, 3 different diameters. So there was and always the version with and without hydrophobic coating, because they might have some impact. And we tested rope like of 8 millimeters, 9.5, and 9.9. So 3 diameters, version with and without hydrophobic coating. So total like 6 versions.
And it performs similarly across all 4 tests.
Yeah, there were some tests. There were like that's really like slight differences in like those thinner ropes, but in general it applies for all ropes.
I think my question comes back to obviously the cut patterns that you're seeing are very different across the 4 tests, which is interesting. But does it matter, if that makes sense? Like, can we get to one test that tells us enough to know that we're going in the right direction with like the next series of ropes and the next series?
Yeah, that's why I think we should investigate in different like real scenarios, because this was actually like on the more side of more like heavier weight and a bigger fall with not that sharp edge. And it will be interesting to see like how it looks like when you have a sharper edge, but like a lower, less heavy climber with less severe fall. And then if we will confirm that the braking mechanisms are the same, then we can try to develop methods which would mimic those braking mechanisms.
Okay, thanks. There was another question somewhere? Yeah?
You partly answered it already, but can you imagine other ways or other natural ways how ropes are being cut? Because you almost like this similar like in the first video.
Yeah. There are like multiple potential scenarios, because some climbing accidents happen over the carabine, which is
There's a groove in this.
yeah, there's like a groove because of friction over years, and then there's a sharp edge, and you actually have like specific cutting, because you can have some fall, but there's no sliding movement. Yeah, with my scenario, there was a sliding movement over the edge, but you can like the dangerous scenario is also when you have a rock fall. So you might have just a impact on some objects, and this may induce slightly different mechanisms or different distribution of them in a sheet and in a core. Yeah, so that's in my eyes, like the way to go in the future.
Okay, one short last question.
Do you know about the speed cutting for those 4 protocols?
Which speed
The
cutting?
speed cutting. At which speed the rope is cut? The duration of the cutting. Does it take longer to cut the rope in one technique in comparison to the other? For instance, the one you test yourself.
Yeah, I don't have any numbers here, but for example, like the method from Mammoth with this pendulum swing, it actually seems like that when the blade touches and cuts just the first few fibers, or like 1 millimeter maybe, the crack kind of propagates through like super fast. And yeah, and for this simulation of the climbing accident, it was like 0.2 seconds. Yeah, so they're like, yeah, those times are different, but also all those conditions in the rope and during the fall are different.
It's just to know if the cutting pattern could be related to the time it takes to cut the rope.
Yeah, that's why I think I would like to try like different simulations of climbing accidents to investigate all those factors.
Thanks.